Now let's look at the long short-term memory methods. LSTM is particularly effective when the data sequence exhibits strong temporal correlation over long horizons. It's better than MLP and RNN for long sequence learning because it can avoid gradient exposure and vanishing issues as the non-memory path doesn't have weights smaller than or larger than 1. This figure shows the internal structure of a single LSTM seal. Unlike a standard neuron, an LSTM seal contains multiple gated components that jointly control information flow through time. At time step t, the LSTM seal receives the current input vector xt together with the hidden state ht-1 represents short-term memory, and the seal state ct-1 represents long-term memory from the previous time step. First, the forgot gate compacts the activation ft, which controls how much information from the previous seal state ct-1 should be retained. This gate depends on both the current input xt and the previous hidden state ht-1. Next, the input gate produces the activation it, which determines how much new information will be written into the seal state. In parallel, the candidate seal input gt is generated through a hyperbolic tangent function. This represents the new information that may be added to the memory. The new seal state ct is then updated by combining two parts. The retained memory ft hard-mount multiplied with ct-1 and the new candidate information it hard-mount multiplied with gt. This additive structure enables stable long-term memory. After that, the output gate computes OT, which controls how much of the internal seal state will be exposed as a hidden state. Finally, the hidden state HT is obtained by applying a nonlinearity to the updated seal state CT, and then modulating it with the output gate OT. The hidden state HT is passed to the next step and can also be used for prediction. The whole seal can be denoted as follows. Now let's look at how to use LSTM for power forecasting. Similarly to the previous case, the historical power sequence was sampled to construct the input feature sequence for the LSTM. This sequence is fed into a stack LSTM structure consisting of multiple LSTM layers. In the first LSTM layer, each block represents one time step. The hidden state dimension is denoted as D1. The LSTM processes the input sequence sequentially and update its hidden state and seal state, which allow it to store temporal information over time. This process is repeated through multiple LSTM layers. By stacking LSTM layers, the model is able to learn higher-level temporal features, moving from row sequence pattern to more abstract representations. After the final LSTM layer, the output hidden state is passed to a fully connected layer. This layer maps the learned temporal representation to the predicted future power values. The output of the later corresponds to the forecasted power value of the future step. An autoregressive structure is also applied to push forward the forecasting. On the other hand, full connected layer can also map to a future power sequence, enabling sequence-to-sequence style forecasting. Next, I present numerical tests using an LSTM model with a double 24 hidden dimension layer structure and a time resolution of 1 hour. This setup is designed for day-ahead power forecasting as before. When the source and target datasets have high similarity, the prediction closely follows the ground truth. When the source and the target dataset are less similar, the prediction accuracy degrades slightly, but the LSTM still maintains reasonable performance in tracking the overall dynamics. However, since the forecasting horizon in this problem is relatively short, LSTM doesn't demonstrate a clear advantage over a standard MLP in this case. In general, LSTM performs better when the input sequence spans multiple cycled patterns such as weekly or monthly cycles. One advantage of LSTM is that it doesn't rely on external time step features, whereas MLP-based models typically require explicit time-related inputs. For the next page, I will introduce how to use TCN for power forecasting.